Okay, so for our next problem here, we're going to take a look at a runner going from, it says a baseball diamond is a square with 90 feet, sides of 90 feet. A batter hits the ball and runs towards first base with a speed of 24 feet per second. Question A says, at what rate is his distance from second base changing when he is halfway to first base? So we've got this runner at home plate here. He's going to run towards first base, and we want to know at what rate his distance from second base is changing. So I'm going to play the video so you can see what's going on here. So as the runner runs, you can see that his distance to first base is decreasing, as well as his distance to second base. Okay? And we basically want to know at what point or at what rate is his distance changing when he's halfway to first base. Okay? So I'm going to let him try and get halfway to first base here. That's going to be right about there. Oops, didn't quite make it, but we can pull this back maybe a little bit. There we go. So that's about halfway to first base right there. So that we want to find out at what rate the hypotenuse is changing as the runner nears closer to first base. Okay? So there's a couple of key pieces of information here. First of all, what I'm going to do is I'm going to label my triangle here because I know that this is 90 feet between first and second. So I'm just going to call that, we'll call that X. All right. Actually, I'll use, instead of X, I'll use B. How's that? Since it's a right triangle. All right, so I'm going to call that B equals 90 feet. I'm going to actually change this because we don't want 66.5. We want to know when this, we'll call this A. We want to know when A is equal to 45 feet. That's halfway there. Okay? And the information given in the paragraph says that the batter is running with a speed of 24 feet per second. So again, keep in mind that our runner is decreasing the distance to first base. So what they're telling us here is that dA dt is equal to negative 24 feet per second. Okay? And again, the reason that's negative is because his distance to first base is decreasing. All right? All right. And then it says, at what rate is his distance from second base changing when he's halfway to first base? So what they're giving us here, what they want to know is based on my picture here. If we're going to label this AB, this is going to be C over here. They want to know what is dC dt when A equals 45 feet. All right, so this is what we want to find. We want to find dC dt when A equals 45. Okay, so here we go. First thing we're going to do is we're going to set up Pythagorean theorem because we're dealing with a right triangle here. So this is part A over here. So we're going to do A squared plus B squared equals C squared. Now, whatever distances are not changing, I can go ahead and plug in right now. So the only distance that's not changing is B. And you saw that in the video before. The distance from home to first is changing. The distance from between home and second is changing. So I cannot plug in for those. So I'm going to go ahead and plug in for B. So that's going to be A squared plus 90 squared equals C squared. And then I'm going to go ahead and take the derivative of all of that. Okay? So if I do the derivative, I'm just going to make this a little bit easier. I'm going to put D, what are we looking for the derivative of? We're looking for dC dt, right? So we're going to take the derivative with respect to t. So that's going to be 2a dA dt. And the derivative of 90 squared is just 0, so we don't have to worry about that. And the derivative of c squared is 2c dC dt. Okay, and so now that we have our derivative, we can go ahead and plug in some values. But the problem is that I know A is 45, okay, but I don't know what C is. So I'm going to need to find C. All right, so I need C when A equals 45. All right, so in order to do that, we're going to do some Pythagorean theorem. So we've got, what do we got? We got 45 squared plus 90 squared equals C squared. If we add 45 squared and 90 squared, I'm not sure what we get, but I do know that if we take the square root of this, 45 squared plus 90 squared, that's going to equal C, and so C is going to be approximately, rounding to 3 decimals here, 100.623 feet. Okay, so that's C. That's what I need when A is equal to 45. Okay, so now that I know C, I can go ahead and plug in. I also need my rate from above, so I need to know what dA dt was. So that was negative 24 feet per second. So I'm taking that straight from the given information. So I know I have 2 times the value of A, which is 45, times dA dt, which is negative 24, and that's going to equal 2 times C, so that's 2 times 100.623 times dC dt, which is what I'm trying to find here, dC dt. All right, so that's my only variable left here. All right, so let's see here. I'm going to take and simply divide both sides. I'll do this in my calculator in a minute, but I'm just simply going to divide both sides by 2 times 100.623. I'm going to divide this side by the same thing, 2 times 100.623. And right away I notice the 2's are going to cancel off, so I just need to punch that in my calculator and figure out what that equals. So when I do that, I end up with dC dt equal to, and this comes out to be negative, which it should, because the distance between home plate and second base is decreasing, 10.733 feet per second. All right, so what does that mean? What did we just find here? Okay, basically what's happening here is the batter's distance from second base is decreasing at a rate of 10.733 feet per second when the batter is halfway to first base, or yes, halfway to first base. Okay, so the distance from the batter's distance from second base is decreasing at a rate of 10.733 feet per second when the batter is halfway to first base. That's what our answer indicates. Okay, all right, so the next part of this then, the B part, so we'll go back up here and look at our picture again. It says in the B part, it says at what rate is his distance from third base changing at the same moment? Okay, so when he's halfway to first base, how fast is his distance from third base changing? All right, so I'm going to draw a little picture here. We're going to get our triangle set up here because again, and I'm just going to use the picture that's up here. So now we're talking third base and the distance from here. Okay, so I'm going to use different variables so we don't get confused. I'm going to do a z for the hypotenuse. I will do x for this leg over here, and I'm going to do y over on this side, and I know that y again is equal to 90 feet. Okay, So this time we want to know what is the rate his distance from third base is changing. Now, if you think about this, I'm going to go back to the picture for a minute. As the batter run towards first, notice his distance from third base is actually increasing. Oops, there we go. Okay, so the distance between third and the batter is increasing, as well as the distance from home to the batter is now increasing. So we want to keep that in mind. All right, so for the B portion of this, we are looking at, again, a right triangle. So we're looking for the distance from third to the batter. So that's dz dt. dz dt equals what when, and in this case we're going to call it x is equal to 45. Okay, and we know that dx dt is equal to 24 feet per second. And again, now since we're looking at a different triangle, this is increasing. All right, so we're not going to be putting in a negative this time. This is going to be increasing. All right, so here we go. Whoa, a little too far there. Let's go back up. All right, so here we go. So this time our triangle is going to be x squared plus y squared. I'm going to go ahead and drop in 90 for y because that's not changing, equals z squared. I'm going to go ahead and take the derivative of that. So we'll put some parentheses around here. And we'll do d dt. So again, we end up with 2x dx dt. The derivative of 90 squared is 0, and then we end up with 2z dz dt. And that's what we're looking for this time, is dz dt. Now, here's the nice thing about doing this problem. I know what x is because x is going to be 45 feet. We were given that. I know dx dt, that's 24 feet. And I know z because I calculated z in the previous problem. Okay? So basically my Pythagorean theorem is going to come out to be the exact same value of z because I was halfway to first base. And so z is going to equal 100.623 feet. Oops, 100.623. All right, so we just have to plug in. So here we go. 2 times x, which is 45, times dx dt, which is 24, equals 2 times 100.623 dz dt. You may be noticing some familiarities to the last problem here. I'm going to take and divide both sides of this by 2 times this value again. So 2 times 100.623. Divide this side by 2 times 100.623. The 2's are going to cancel off again, and guess what? It turns out the dz dt is equal to positive 10.733 feet per second. Why are they the same? Because he was halfway to first base. So the distance from third base is increasing at the same rate that my distance from first base was decreasing. Okay? So we would say that the batter's distance from third base is increasing at a rate of 10.733 feet per second when the batter is halfway to first base. Okay? So hopefully that makes sense there, and we'll keep moving along here. Okay, so our next problem, if you flip the page, talks about at noon, ship A is 150 kilometers west of ship B. So ship A is the blue one on your left, and ship B is the one on the right. Ship A is sailing east at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 p.m.? Okay, so when I do this one, I want you to watch the ships, and then as it starts over again, I'm gonna let you watch the graph as well. So watch the ships first and see what's going on here. Okay, so they start sailing. The blue ship is getting closer to the point where ship B was. Okay, and ship B is getting further away from that point. And if you notice, as ship A continues towards the west, ship B continues north. You can see the rates: 25 kilometers north, negative 35 kilometers to the east. That's because the distance is decreasing with the green line, but the blue line's increasing. And if you watch what happens here, as the blue ship gets closer to ship B, the distance between the ships decreases. Watch the number here on the red line. And then all of a sudden the distance starts to increase again, which means the ships are now getting further apart. And you can see that on the graph to the left, where the point comes down the graph. So the distance is decreasing between the ships as the time goes by, and then all of a sudden, when they get to a certain point, even though ship A is getting closer to the point where they started, ship B is getting further away. So watch the point on the left side here. It starts to go back up. So as time is increasing, my distance starts to increase again. All right? So our goal here is to figure out how fast is the distance between the ships changing at 4 p.m. Okay? So at 4 p.m. All right. So before I go too far, I need to write down some given information here. Okay? So I know, and I'm going to have to do a different triangle here on this one maybe, just because the numbers on there might get a little confusing. So let's do that first. So I'm going to take the information, I'm going to draw a new triangle here, and I'm going to label my triangle. So we're going to label this side as A, this side is B, and then the distance between them we're going to call C. Okay? Now it tells us that ship A is traveling this direction. Okay, so they're giving us dA dt, and dA dt is equal to 35 kilometers per hour, but what we notice is that that distance is decreasing. Okay, so this one needs to be negative. The 35 here has to be negative. Okay, and then they also tell us that dB, the rate of boat B, is 25, so we're going to call this one dB dt. This one is 25 kilometers per hour, but as ship B sails north, the distance is increasing from the starting point. So that one is going to stay positive. Okay? So those are the two rates that were given. It does talk about the fact that the ships are going to sail for 4 hours. So if we look at how fast each one is going, after 4 hours, ship B is going to be 100 miles away. And after 4 hours, ship A is going to equal that. Well, we got to be careful here because the distance is decreasing here. So we need to be careful. It says that at noon, the initial distance, so at 0 hour, the initial distance was 150 feet, or excuse me, 150 kilometers. So that means that if ship A sails for 4 hours at 35 kilometers, I need to take 150 kilometers and I need to subtract 4 hours of sailing time. Okay, so hopefully that makes sense with what's going on here. So A is equal to 150 minus 4 times 35 mile or 35 kilometers. I don't like kilometers. All right, so A is going to equal 10 kilometers. All right, so what we need to find here is we need to find dc dt. Okay, so let's see what we got going here. We're going to start off with a little Pythagorean theorem. All right. All right, so let's, I'm going to keep working down to the right here, but I'll change colors here. All right, so I know that, again, Pythagorean theorem, a squared plus b squared equals c squared. Now, this time, a is changing, b is changing, and c is changing, so I cannot plug in anything for any of these. So I'm going to go ahead and take the derivative of each one. So that gives me 2a dA dt plus 2b dB dt and that's going to equal 2c dC dt. Alright, so there's my setup. I have 6 variables in that problem. I've got A, I've got dA dt, B, dB dt, C, and dC dt. Now, I know what A equals, I know what B equals, I know what dB dt is, I know what dA dt is, I don't know what C is. So I'm going to have to do Pythagorean theorem to find C. Alright? So here we go. In order to accomplish this, let's switch colors again so we can see that we're doing something different here. So I need to do 10 squared plus, what do we say B was, 100 squared equals C squared. Alright, so the left side, that's going to be, that's going to be 1,000 plus 100, that's going to be, it's going to be 10,000 plus 100. Okay, so this is going to be 10,100 equals C squared. And I'm just going to go ahead and pull out a calculator again here. So C equals 100.499. And so now I know A, B, and C, and I know dA dt and dB dt. Alright, so let's go back to my formula again and see what we got here. Okay, so how much room do I have here? Well, not very much. Let's go back up here. Okay, so I'm going to come up on this side of the right. So actually, before I do anything here, you'll notice in my formula I've got 2a, 2b, 2c. I'm going to divide that whole thing by 2. Okay, so if I divide the whole thing by 2, then the only thing left is a, and then dA dt plus b dB dt, and then that's going to equal C dC dt. Alright, so now let's plug in. So A, we said, was, let me make sure I got all these right here. Okay, A was 10 kilometers. Okay, so there's A, 10 kilometers, times dA dt, which was negative 35, plus B, which is now 100, times dB dt, which was 25, and then C, we figured out, was 100.499 times dC dt. Okay, so there's our setup. On the left side here, we get negative 70 plus 2,500 equals 100.499 dC dt. And if we add these guys up, that's going to give us, I might have to stop and get out a calculator here. This is going to be 2430 equals 100.499 dc dt. And so if we divide out the 100.499, we end up with dc dt equal to 21.393. Now we're talking kilometers per hour here. And the reason my answer is positive is because, as you saw in the video, the distance between the boats actually starts to increase after a certain time period. At first the distance is decreasing, then after a while the distance starts to decrease. So what are we saying here? We're saying at 4 p.m., okay, the distance between the ships is increasing at a rate of 21.393 kilometers per hour. Okay? Not too bad on that one, is it? Okay? I'm going to get my next problem set up here. Okay, so here's our next one. Okay? So it says a rocket flies vertically at a speed of 4 miles per minute. You are watching the rocket from a distance of 30 miles away. Okay, so you can see at the bottom of the graph here it says horizontal distance in miles. So you're basically over here at 0. The rocket's 30 miles away. At what rate is the angle of elevation to the rocket changing after 12 minutes? Okay, so we want to know, this time we're talking about the angle. So if we go ahead and watch the video here, you can see that as the rocket goes up, the angle between the rocket and the ground increases, and you can see that with alpha down here in the lower left corner. Okay, we want to know what the rate, at what rate is the angle of elevation to the rocket changing after 12 minutes. So we want to know, I'm going to try and stop it here. Okay, that's pretty close to 12 right there. So the angle at that point is right around 58 degrees, but that doesn't tell us at what rate that angle is changing. Okay, so just seeing the angle there doesn't really help us. Okay, so what we're going to do is we're going to go back and we're going to talk about how to find the rate at which this angle is changing. Now you'll notice as the rocket goes up, we're basically creating yet again another right triangle. But the difference this time is we're talking about an angle, not about a side length. Okay, so here we go. We're going to go back here. I've already kind of drawn in the triangle so we can see what's going on here. We have some given information. We know that the bottom of the triangle is 30. Okay. That's my dog in the background there. Okay, so we've got at the bottom of our triangle, we're going to label as 30, and this is in miles. And it says the rocket flies vertically at a speed of 4 miles per minute. And then at the bottom it says at what rate is the angle of elevation to the rocket changing after 12 minutes. So after 12 minutes the rocket's going to be 48 miles in the air. So this length here is actually going to be 48. Okay? Now, if you keep in mind, I'm going to label, we'll do A, B's, and C's here. So we're going to let this guy be A. But what we have to keep in mind here is which values are changing and which values are not changing. Okay? Distance B is not changing. So if I do anything, I can plug that in. Distance A is constantly changing as the rocket flies north, so I cannot plug anything in for A at this point. Okay? And our speed, so our dA dt, okay, so the rate at which the rocket's going, dA dt, is equal to 4 miles per minute. So there's our units right there for this. Okay? And it says, at what rate is the angle of elevation to the rocket changing after 12 minutes? Okay? Now, the 12 minutes affects the A value, so we don't really need to worry about the 12 minutes once we know that A is going to be 48 here. All right? So there's our picture, there's our setup, and what do we need to do with this? Okay? We're not going to do Pythagorean theorem this time because Pythagorean theorem doesn't talk about the angles. So you notice this angle in the corner here, this is labeled as alpha, so I'm going to leave it as alpha. Okay? And again, what we need to keep in mind is this letter B, okay, this distance is not changing. Distance A is changing, and distance C is changing. Both of those, A and C, in a positive value. Okay? So I don't want to do Pythagorean theorem here. I need to do some right triangle trig here. Now you've got three choices for right triangle trig. You could do cosine of alpha equals A over, not A, B over C. You could do sine of alpha equals A over C. Or you could do tangent of alpha equals A over B. Now, how do you know which one to pick? Here's the thing. B is a fixed number. So if I can do something with B, it's going to be easier than choosing something with A and C because A and C are both changing. All right? So I'm going to choose tangent because having A in the numerator is easier than having, for instance, if I did cosine of alpha, having C in the denominator and trying to take a derivative at some point. Okay? Hopefully it'll make more sense when we do it. So I'm going to use tangent of alpha, and that's going to equal A over B. Again, A is changing, so I can't plug in for A, but B is fixed, so that's just 30. All right? And so now, I think what I'm going to do, just the A over 30, I'm going to rewrite this just so it makes a little more sense when I do the derivative, but tangent of alpha, A over 30 is really just 1/30th A. Okay? So you'll see what I'm talking about here in a second. All right, so here we go. Taking the derivative of both sides. All right, so we're going to do d dt, d dt. So I take the derivative of tangent. The derivative of tangent is secant squared. So I have secant squared alpha times the derivative of the inside material. Now remember, when you take the derivative of tangent, we're always taking the derivative of the inside too. So first of all, it's secant squared alpha, but then we're taking the derivative of alpha, so d alpha dt. Okay? And if you go back and read the problem, it says at what rate is the angle of elevation changing? That's d alpha dt. Okay? Take the derivative of the right side, and the derivative of 1/30th A is just 1/30th times the derivative of A with respect to t. All right? So you can see we have three variables in here. We have alpha, we have d alpha dt, and we have dA dt. I was given some of that information. I was given dA dt, and I was given, where's my other numbers here? It looks like we're going to have to find secant of alpha, doesn't it? I do not know what secant of alpha is. Okay? So we're going to have to go find that in order to plug that in, because again, our goal is dx dt. All right. So I need to find secant of alpha. All right. So I think I'm going to draw another triangle here just so we can see what's going on. Okay. So I know that this side is 48. I know that this side is 30. I know that this is C. I know that this is alpha. And I need secant of alpha in order to plug into my formula. All right? In order to do secant, I know that secant of alpha is defined as hypotenuse over adjacent, so I need to know C over 30 in order to do secant. So in order to find C, we're going to have to do Pythagorean theorem here. Okay, so I've got 30 squared plus 48 squared equals C squared. If you add those two together and square root both sides, you get C equal to 56.604. Okay, so now I can say that the secant of alpha is equal to 56.604 over 30. Okay, so that's what I'm going to plug into my formula. So now I know secant of alpha and I know dA dt. So I'm going to go back over to my formula now and I'm going to continue along here. So secant of alpha, replacing that with our fraction over here, this is going to be 56.604, 604, divided by 30. Notice it's secant squared, so we got to square this. This is times dxt, or d alpha dt, my alpha looks like an x, equals 1/30. And dA dt again was 4. That's not so bad. All right. So we're going to need a serious calculator here. All right, but let's do this. I'm going to simplify the right side. Let me see. We got 56.604 divided by 30. This whole thing's being squared. D alpha dt equals 4 over 30. Now, if you look at what's going on here, in order to get rid of this 56 over 30 here, I can divide it out, or I can multiply it by the reciprocal of this. So what I'm going to do is I'm going to take and multiply both sides by 30 over 56,604 squared, because that squared is attached to both parts. So d alpha dt is equal to 4 over 30 times 30. Now again, keep in mind that both of these are squared. This is 56.604 squared, and this is 30 squared. All right, so that's 30 squared over 56.604 squared. Now, I'm gonna finish this without a calculator for one reason only here. Number one, I can cancel off the 30s here, so that those are gone. And then I can multiply 4 times 30, because that's pretty easy. So d alpha dt is equal to 4 times 30 is going to give me 120 over 56.604 squared. Now, if I just leave my answer like that, now obviously I've already pulled out the calculator once, but if I leave my answer like that and I attach the right units to it, I'm okay on an AP test. I don't need to get it down to the exact value of what's going on here. So I could literally say that this, remember, alpha, that's an angle. Our angles are in radians. So our angle is changing at 120 over 56.604 squared radians per minute. Okay, so hopefully that kind of makes sense in what I'm doing there. I'm just not simplifying. If we simplified it, we would actually get d alpha dt is equal to 0.037 radians per minute. Okay, so I hope that makes sense, and good luck. What are the problems here? We got some problems down at the bottom. Oh no, I guess I'll see you next time. Bye-bye.